Do we have a volunteer in the first one? Okay, good. Okay, then you are welcome to clear your presentation here. In the meantime, please give me your hard copy of the slides. Thank you. Okay, so again, every team has only 20 minutes. Are you doing something? So every team has 20 minutes to report your term project, okay? So when the time is 15 minutes, there will be a ring to remind you. And 18 minutes, there will be 2 rings to remind you that there are 2 minutes left only. Okay? When the ring is 3, 1, 2, 3, ring, that means time's up. So you have to go, you have to step down in that sense. Okay? All right, thank you. First.
Today we are going to introduce a method for estimating the position and orientation of accelerometers using only their own signal outputs. No external measurement tools are required. This work is collaboration between me, Qijun Tang, and my colleague, Xin Hong. Our presentation is divided into 2 main parts. Then we'll conclude with our expected outcomes in the final remarks.
This project proposes a self-contained method to identify the position and orientation of accelerometers only using their signal outputs, that is, no camera tracking and no external markers. The key ideas are: we don't rely on any external measurement systems. Instead, we use the principle of rigid body motion and perform numerical optimization to solve the unknowns. This method is especially useful in structural dynamic testing, where many accelerometers may be employed across a surface. It provides a low-cost, efficient solution that's ideal for analyzing small-scale vibration. Introduction. Accelerometers are widely used in vibration analysis and structural dynamics, such as in buildings, bridges, and machinery. However, traditional approaches for positioning these accelerometers rely on manual alignment or optical systems, like motion capture, which are expensive, time-consuming, and not scalable. Our approach offers a self-contained solution that reconstructs each accelerometer's relative position and orientation using only their signal data plus some physics. Comparison with the existing method, SCAA. These Venn diagrams compares our method to conventional techniques. For example, the techniques like SCAA requires synchronized cameras for laser systems. Our method, by contrast, works entirely from within the system, relying only on inertial sensor output, making it is easier to apply in real world and constrained environments.
To understand our method, let's start with the assumption of rigid body motion. We assume that all accelerometers are mounted on a rigid structure, meaning the relative distance distance between them does not change even during motion. We describe rotation using a tight right angle convention, which consists of yaw, pitch, and roll. The total acceleration at each point is composed of translation acceleration and rotation acceleration and correlate acceleration. And possibly, low, this is typically negligible. This image illustrates the three tight right angles: yaw rotation around the vertical axis, pitch rotation around the side axis, and roll rotation around the forward axis. We use these angles to describe how each sensor moves and rotates in 3D space. These angles will later be optimized to fit the measured data. This schematic shows a typical rigid body. When one part of the object moves, the others follow accordingly without distortion. In our context, each accelerometer experiences a unique acceleration, depending on its position within the body and the nature of the motion. And that's the key clue we use to reconstruct their relative positions.
To validate our method, we first recorded data using mobile sensors and the app Firefox, which allowed us to collect raw accelerometers and gyroscope signals. These 5 slides show sample readings from multiple charts. Each chart corresponds to either accelerometer or gyroscope data from different axes and time intervals. Here, for example, we see distinct patterns across the sensor, which arise due to different spatial positions and orientations. These raw signals are the only input our algorithm used to determine where each sensor is and how it's oriented. After recording, we exported the data into Excel for further analysis. The left figure shows the angular velocity from the gyroscope, and the right figure shows the acceleration data. You can already notice some clear trends, which indicate both translational and rotational motion. We'll make use of that in our mathematical model.
To test our model, we wrote a simulation in MATLAB. On the left is our MATLAB code, which generates accelerometer signals based on a rigid body, undergoing both translation and rotation. The output on the right shows the simulated acceleration values at different time points in position. In this section, we introduce the optimization framework used to estimate the unknown accelerometer position and orientation. Step 1 is to define the error function. We compare the measured acceleration values, denoted as a step measure, with the theoretical acceleration computed from our rigid body model. The cost function is the sum of square residues. Step 2 is to minimize this cost. We use gradient descent or MATLAB's nonlinear least squares solver to find the optimal parameters. The result is the best estimate of the 3D position and orientation of the accelerometer. Here is a sample simulation we use to validate the estimation. We simulate a non-sensor position and run the optimization to recover it. The figure on the right shows how the RMS error reduces over iterations, eventually converging. This indicates that the method is effective even with added noise. This plot shows a 3D error surface, where we vary two position parameters to visualize the cost landscape. It shows that the cost function is relatively smooth and convex near the true value. This property ensures that even a rough initial loss can coverage eventually using guarantee-based solvers. To estimate position, we use the rigid body acceleration model, where omega is angular velocity, and alpha is angular acceleration, and r is the unknown sensor position. We minimize the difference between measured and modeled acceleration using MATLAB's Bitcoin solver with both constraints. The figure shows the estimated position after coverages. Now, let me explain how we estimate the sensor orientation. We start by assuming that the gravity vector is known. Using this assumption, we try to find a rotation matrix, or theta. That minimizes the difference, or residues, between the model stated acceleration and the actual measured acceleration from the sensor. The optimization variables here are the z, y, x, u, y angles, which represent the rotation. The plot shows how the accuracy of this estimation improves steadily with each iteration of the solver. To make our orientation and position estimation more robust, we apply several filtering techniques to the raw sensor data. First, a bottle low pass filter with a cutoff frequency below 20 Hz reduces high frequency noise. Then we smooth the signal further with a moving average filter. Finally, we fuse these filter signals using a comma filter, which combines data and reduces noise effectively. After filtering, the acceleration signals are much smoother, and the estimation errors drop by approximately 30%. Here we compare the errors before and after filtering. Without filtering, the position error is around 1.5 centimeters, which decreases to 1 centimeter after filtering. For orientation, the error reduces from 3.2 degrees to 1.8 degrees. These results clearly show how the important processing and filtering are in improving accuracy. Adding more sensors generally improves accuracy, as it provides more information for the estimation. Among different filtering methods, common filter performs better than Butterworth or simple moving average. This insight will help us design more effective experience in the future.
Now, I wanted to highlight some extended discussion and plans for future work. First, our current optimization uses the squared L-2 norm, also known as least squares, because it is mathematically simple and the solver converges quickly. However, this norm is sensitive to outliers and abnormal noise in the sensor data. To address this, a more robust alternative is the Clover loss function. It behaves like L-2 for small residuals, but switches to L-1 norm for larger residuals, making it less sensitive to outliers. Future work will involve comparing these loss functions and their effect to estimation robustness. Second, a fundamental question is whether we can uniquely identify the accelerometer's position and orientation from acceleration data alone. This depends heavily on the richness of the motion performed and sensor placement. If the motion is purely translational without rotation, the problem is underdetermined, and we cannot get unique solutions. Sufficiently rich a rotation motion across multiple axes and good spatial distribution of sensors are both necessary to guarantee identifiability. Finally, we performed a simulation combining translational and rotational motion to test our algorithm validity under realistic conditions. The result confirmed that our method converges well and can be used as a benchmark for real-world sensor data. To test the method in realistic conditions, in realistic scenarios, we simulated a complex motion trajectory that includes both rotation and translation. The plot on the right shows the resulting acceleration trajectory. This test verifies that the estimation method remains stable and reliable even under dynamic motion, not just static calibration.
To conclude, we presented a method to estimate both the position and orientation of the accelerometer using only motion data. The method eliminates the need for external tracking devices or markers. It is based on rigid body dynamics and solved via numerical instructor. The approach shows promising results and can be applied in structure testing, robotics, or vibration analysis. These are the core references used in this project. The primary methodology is based on the 2020 paper by Cherniak and Swab, which introduced a framework to estimate accelerometer positions and orientations from their signals. We also consulted Koch et al. For general orientation estimation using inertial sensors, and Rahman et al. For rigid body accelerometer only method. Full citations can be found at the end of the report and paper. Okay, thank you for your attention.
I think you spent lots of time on this project, and you did a good job. But a few points I want to remind you is, number one, in the slides, yeah. Usually for the slides, we don't need to put a table of contents, okay? The table of contents. The second page. It is not really necessary. Okay? You don't have so much page when you present the paper in the full of contents. Okay, but right, that's another point. And then in your proposed method, you mentioned about like the moving average, common filter, so and so. It's better to give a slide to describe what is your mathematical model for a common filter. Okay, it's very important because different model will yield different common filter algorithm. I mean, the dynamic model will be different. So you have to show the dynamic model, mathematical model. What's your mathematical model? For example, in the page number, let's see. What's this one? This page. There's this one. What's your R of theta? What's R of theta here? You show the equation, but you don't get the details about the position in the matrix, okay? Position vector, R of theta. What's that? Okay. And that, I think that will be implemented in your common filter algorithm, right? Okay, so things like this. And also, in the figure here, next few pages, this one. You have two strips,
Yes.
okay? But which one is which one? I mean, it's not so clear. Which one is before the filter? Which one is? Yeah, okay. Especially use different patterns, different colors, different whatever. So that we can tell the difference. Okay, this is for the one before the filter, and this is for the one after the filter. Okay, all right. And then, again, when you are talking to the audience, face audience, we are the audience, not the table. Okay? But you have to practice. Yeah, I have to practice. Okay? But basically, you did a good job. Thank you. All right, who will be the next team? Come on, gentlemen. Gentlemen. Okay, we have a volunteer. Good. You'll be next. After that. Okay, may I have your copy of the slide? Thank you.
Okay, so this is our research. Our title is Application of Physics Constraining Dictionary Learning Method in Vibration Signal Compression. And skip the contents. Okay. This, our research is focused on how to effectively compression the vibration signal data while considering actual sampling constraint. This research describes a physics constraining dictionary, we call it PCDL method, aimed at effectively compression vibration signal while adhering to real-world basis sampling. And by gently improving the measure matrix and the dictionary matrix, the method addresses challenges posed by real-world conditions. In the monitoring of rotation dictionary, continuously collecting and analyzing vibration signal is a critical of fault detection and safe operation. However, the large volume of data poses significant challenge in terms of storage space, transmission bandwidth, and real-time process. Therefore, we need to develop methods that can effectively compress data while retaining important diagnostic information.
The second part is wrong. We will introduce compression. What is compression? It's through the velocity of signal and used in real sample to reconstruction of the signal. We will introduce the dictionary learning. What is dictionary learning? In this paper, the author mentioned is KSDB. So it will update the data database to update our dictionary and return. And our dictionary will become more better. And its reconstruction origin signal effective. Okay, what is physical limitation in sample? So in real world, it cannot have a continuously sampling between the time intervals, and the right way is to be a time gap between the sampling point. So we'll call I prefer to call it ideal condition. Okay, the third part is proposed method. So we'll have three limitations. First is we fix the style. We use style to optimize file. And the second is gamma less than t sub 0. And t sub 0 it means the non-zero element. So if it's greater than t sub 0, it will be it's didn't work. And the third is I of phi greater than r. It's the time interval between two samples. So it's greater than r. Oh, and it's greater than r. And the symbols meaning S is original signal matrix. And second is psi. Psi is dictionary matrix, or also it can call basic matrix. And Y. Y is the sparse coefficient matrix. And Y is the gamma matrix. Okay. And the phi is measurement matrix. And R bar is called trait of parameter or weight condition. So it's balance the first part and the second part. The second part. And T sub 0 is the non-zero element. And the R is the minimum time interval between two systems. Okay, next. Okay, and the first stage optimization. Okay, what is first stage optimization is we will fix time to optimize file. Okay, and this one is we'll introduce later. Okay, so this one edge of side is lambda square, and lambda is the eigen value. Okay, so next. So what we do? So edge of this one is the original. The original sample. And this one is the original sample to reduce the signal we don't need. So in this one to minus this one, and we have the redundancy signal. Next please. Okay, that's this trigger. This is redundancy signal. So if we want to end sampling point, we reduce n minus n point. N minus n point. Then we have the point we need. Yes. So we reduce the maximum point and return. We have this one, measurement matrix. And the one is the each each edge is a time point. We test. Okay, next. Okay, second stage. So we will pick 5 to optimize style. Okay, next. Next. Okay. So this figure is KDA. So we will go that way. So we have Y equals YS. And the Y is the data we have, we measure. The Y is measurement measure. So we want to look for S. But S is not the quantity signal. So we use the quantity way to find S. So we can S with psi gamma. And we have phi psi gamma y. We have y, phi, and psi. And this one is called sensor matrix. We can find gamma. And we use gamma to multiply psi. Psi multiplied gamma is equal to original signal. So we will return this step. We will return it. And we can find the original signal. Okay, next, please. Okay, and this one is the original signal and the reconstruct signal error. It's like the border norm. This is the sum of the error. And this one is multiply phi. It's the compressed signal and the compressed reconstruction signal error. Okay, next. Okay, experiment. So we have sampling at 24.6 kilometers, and we have this one. And we use x direction and y direction. We have the 11,000 into 1,150 segments. And each segment has the 100 point gauge. So we use 100 point gauge to select the random sample. Okay, such as 35 point we select. And we have the beginning. We have the state of the beginning, middle, and the near end. Okay. Next. So it's the original signal. It becomes more failure or more function. So we use this two line, the middle is left to ruling like this. That is time domain, T domain. And we use Fourier transform to become frequency domain like this. Okay, next. Now why we use Fourier transform? Because the Fourier transform will become the bandwidth becomes narrow. So it's affected. Okay, next. Okay, we use Fourier transform to have 6 different frequency domain signals. And frequency domain signal will transform to the time domain. 6 different frequency interval. 6 different frequency interval. Okay. Next, please. Okay, so we will put this 6 into a dictionary, and we have the optimized dictionary matrix. Okay. Next, please. And we'll select one to be a measurement match. Oh, which one is the better? The better will be. That it becomes the measurement match. So it's the error. Like we have 35 points. We have 100 data points. So the comparison ratio is the 2.86. And put this into the error formula like this. The error of this experiment was 0.024%. Okay, like this. Okay, so the important the error is 0.0024%. It's less than 1%. So its reconstruction is great. It's successful. And high reconstruction. Next.
Talk about two keys. The first is a KSE, and the full name is squad error. Like it. MSE represents the coordinate difference between each point of original signal and a reconstructed signal. So SI is the original signal's point, random point, and Y is the reconstructed signal's random point. And so if we have the FSE's number is close to 0, then so that means the original signal is close to reconstructed signal. That means it's like no error. And if it's bigger than 1, then that means it's very bad constructed. And the second is a SNR. It's a signal to noise ratio. The SNR is used to evaluate the rotation of signal reconstruction to simplify the extent of noise interference. A higher SNR indicates a stronger signal relative to noise, meaning better reconstruction, and the lower SNR implies more noise contamination. So if the SNR is below to 0, it means the signal is almost entirely overwhelmed by noise. So in the SNR formula, the nomenclature representation the square energy of the original signal, or the demolition reconstruction energy of the reconstruction error. And this, the S is the demolition demonstrator is the energy of the original signal, and the next one is a demolition. So I'll break that. So this is the figure after we added command. So we can see the left side is the blue line is the original signal, and the red line is the line before the dictionary update, and the right side is the pink. I'm not sure it's pink. So it's a line after dictionary update. So we can see it's better before it, and it's more closely to original signal. So in the photo we just see, the MSE decreased 93% from 0.23 to 0.01. And I mean the intuition of significant reduce in the reconstruction error is more like the original signal. That means its reconstruction is very good. And the SNR before that is 3.44, and after is 60.49. So that means it also means its reconstruction is very well, very good. And this is our magnetic pole. I'm not sure if we need to read it or explain it.
Okay, you explain.
Okay, so
Maybe you just point out again right here.
okay, so like we first create the basic matrix and the side, and we added this is the original signal, the sign, and we add some random point that gives you more like real world signal. So it will not like a usual sign, you will have some weird point on it. And add some, and we choose only 20 points to reconstruct it, and we use it to reconstruct. And just create, excuse, draw the picture, and we edit. So the A part, without considering the physics constant. In reality, such a measuring memory signal series sensor. Series sensor requires time to switch to the next input, and data acquisition system have a minimum time resolution. And physically, there must be a central time interval between simply points. So it's a table. If we have considering the physics constant, and there must be a minimum distance between the simply point. But if we don't, we will freely select the most important point. And this is a future workup. So the PCBL method provides an exactly solution of correlation signal compression, balancing compression rate and reconstructed accuracy and physics feasibility. In the future, the framework will be explored for higher dimensional data, such as image and video, and even it can work on some health or company as well. And this is a reference.
Okay, comments, okay? First one, again, it is not really necessary to give context. Because in a formal presentation, I mean, conference presentation, you don't have that much time to go through the context. It's not really necessary. If you want to say that, use your mouth, speak up. That's it. Okay? You don't have to spend pages on the slide. Okay? And then say like this abstract, introduction, and so on and so on. In the first few pages, page 1, page 2, page 3. Okay, also some other page gap here. It's better to itemize that. You have itemized that, but try to reduce the words. Okay? Highlight the key points. Okay? Because you have to know that everyone. When you are talking to your audience, you are not lecturing the audience. You just give you your key ideas to your audience. Because we as audience cannot read your slides. Honestly, we can only follow your idea, and that's it. So it is better to just highlight your key points. Use a few words to express what you want to say to the audience, and that's it. Okay? Try to reduce the words. Okay? Good. And then basically, I think you also spend lots of time on the project, I think. Okay, you did a good job, okay? But then again, I mentioned that last time. For example, on page 11, you have a Y, the coefficient, sparse coefficient matrix. And you wrote down on the board, not on the chalkboard. But if it is possible, you can put it just right next to the definition. If you have enough space, you can do that. Okay? Make it clear to the audience. Okay, and then also, I'm not sure if that's a typo on equation number 3. Below number 3, equation 3, on page 7, 14, page 14. Yeah. Lambda I is the eigenvalues of psi times psi or psi times psi transpose. Conjugate. Okay, psi star. Okay. So that should be psi star. Because it can be complex. It can be a complex matrix. Or we are talking about so that would be a transpose or complex star. It really means star. Okay, psi star times psi. The psi star. Complex conjugate transpose. Like no, I mean that, what is the size times psi, or psi plus times psi? Oh, psi multiplied conjugate of psi. Okay. Complex conjugate, you mean?
Actually, I don't know why.
You have to make that, to try to understand that, okay, try to clarify that, I mean, because you are using that as a very important one of the then okay? Either, because I think you are talking about the singular value. Singular value, that's eigenvalue of, because in mathematics, remember that we were talking about this now, right? If lambda is the eigenvalue of matrix A, we mean matrix A. That's eigenvalue. But if we are considering singular value, then that is the eigenvalue of A times A transpose. Okay, so that's another point I want to mention. And then later on page 21, equation number 4, you use Frobenius law, F, the subscript F. I think that's Frobenius law. Frobenius law, okay. What if, I'm not sure I can try that. What if we use a very regular, say, 2 nodes? Frobenius was 1 node, or maybe not. Maybe you have to define that first. Okay, maybe that's 1 node. Frobenius node.
It's the sum.
Okay, the sum of the, okay. So, first one, you have to define the node you are using. What is the Frobenius node? Or you have to, or you can explain that using your expression, or oral statement, to represent, to explain what the F stand, what the subscript F stand. It is Frobenius node. Then what is Frobenius node? Well, define that first.
So just state what is proposed.
Yes. Okay. And also, I would recommend you to try if you are interested. Try to use different nodes. See what will happen. Okay. Maybe 2 nodes or every node or whatever. See what will happen. Usually they will be equivalent in some sense. Okay? But from my personal experience, 2 nodes for the Euclidean node, 2 node, Euclidean node, and the node square. I mean the distance square will give us a smooth gradient. Okay, so that's another point I want to remind you. Okay? And then finally, don't have much time, okay, finally. Again, this is talking to everyone, okay, including the first team. it is not really to mention about the future work. Even though we try to do that, but I was reminded when I was a student, you don't need to say your future work to the audience because it has not happened yet. Why you say that? Right? This report is only report what you have done up to now. The future work, leave the future work to the others. Okay? Maybe your colleagues or your classmates. Right? So it is not really to put future work in the slide. Even though we did that, I mean, I did that too. And I was reminded, do not put future work in your slide. Okay? Just a suggestion here. And then the reference, again, I think you have to be careful here. Whenever we are giving a reference or references, it's better to give a complete reference. Means, for example, let's see, the second reference. This is coming from a journal. It's a journal paper. Okay? Now, each conference or each book or each journal has a very specific format for reference. This one is not really belong to any one of them. Say, I told you that, for example, you can use IEEE format, IEEE format, okay? You can use AIAA format, AIAA, or IEEE, or something like that, okay? Again, each conference or each journal or even book, they have their own format for references. We have to follow their format. We do not create our own format. Okay, unfortunately, we have to follow the convention. People use kind of standard format. Right? Okay? You can try to look at, say, IEEE format, see what will give. Okay? IEEE, IEEE, or AIAA. Okay, for example, for IEEE format, you are supposed to give not only the title of the paper, okay, but also the page number, item number, volume number. Those are very important because later on, if someone like me or you want to find out the paper, where can I find the paper? I have to know when the paper is published. I have to know the volume number, or even the page number. Right? Okay? Got it? All right. Thank you. Good. Thank you. Good job. Okay, I believe that we have the next game, third game. Okay, thank you. Be careful of the So who will be the next team? Okay? Good. Okay.
everyone. My name is Yoji and my teammate is Dale. Now we are about to give the final presentation, and our title is New Results on Multi-Agent System Consensus Graph Signal Processing Perspective. Okay. Next. In the mid program, we have introduced the consensus problem of multi-agent system. So today we will still gonna talk about same thing but different. Here's the here's a brief introduction. We will start from the perspective of graph signal processing. The paper established the direct connection between a batch consensus in MAS, aka multi-agent system, and the graph signal filter by interpreting the consensus protocol as graph filter. As teacher asked, we do a kind we separate the report into 7 parts, which are consensus in MAS, graph Laplacian and multi-agent consensus as a graph filter, and new perspective, and take 2 cases, then design the MATLAB file to implement, then compute it. From the last presentation, you only know in MAS each agent is only receive information from its local neighborhood. Yet the objective is for the entire network to reach all ends of the agreement on the specific parties of interest through some mathematical approach. But if you see GSP, graph signal processor filter, you can actually get the same result. To let you know, to let you understand easily, I made a brief picture. So basically, you can imagine GSP as a huge function. There are 2 major frameworks in GSP. The number one is the agency-based framework, which builds on the Jordan normal form and generalize the eigenbasis of the agency matrix. And the second is Laplacian-based framework, which integrates the algorithmic and spectrograph theory with classical signal processing. In this framework, the eigenvalues of the graph Laplacian are interpreted as graph frequencies, and the corresponding eigenvectors from the basis for the graph Fourier transform, as known as GSP. And this paper focuses on how the graph Laplacian spectrum can be used to design consensus protocols. So specifically, the paper revealed that the reaching a virtual consensus in a multi-agent system is mathematically equivalent to design a low-pass filter. That's teacher tell us a few weeks ago. That's receive only the 0 frequency components and 2 higher frequency components. This allows the system to smooth out the individual agent different and coverage to average values.
So before we continue, why do we continue keep research in multi-agent system? Because it can be a solid basis for different industry. For example, aircraft industry or even bioengineering industry. That's why we keep researching on this. So here is a brief review from our previous research. So what is adjacency matrix? It's encoding the connectivity of the graph. So we can see from the first row, we can see it means the connectivity of each node. So the first node has only 2 connections. So it means what? At the second row, here. And the second one has 3 connectivities. So yes, 3 in the value here. And the degree matrix is the diagonal matrix of vertices degrees. And the Laplace matrix is simply the degree matrix subtract the adjacency matrix. And the agent dynamics simply is the formula as below, and it amplifies. So this is the value of agent I in the future. We assume time at k is present, so time k plus 1 is the future. So it's the future value of one entity, and xi of k is the present value plus one user input. So then the user input is defined as below. It simply means for all agents, the value between each neighbors. So this is the particle filter. It's defined as below, and simply speaking, it is just from time k equals to 0 to t minus 1, we keep filtering the eigenvalues of the graph until it gets the ideal frequency. And as we mentioned earlier, the graph filter, we can use it in multi-agent system dynamics. So again, x of k plus 1 is the value in the future, and equals this thing is the filter times x of k, the present value, equals the v diagonal, all this thing, which simply speaking is all eigenvalues are being filtered. And as we mentioned before, a Laplace matrix is the degree matrix minus adjacency matrix. And to get the eigenvalue from a Laplace matrix to do the filtering, we need to use the decomposition, eigendecomposition, to get the value. V is the eigenvectors, and this lambda is the set of the eigenvalues. And as you can see, exact consensus in t-step is achieved if h of 0 and t equals 1. Ideal consensus is basically, usually, is 1. Frequency equals to 1. And we may see in early previous pages, the absence of k is a constant, vary over time. So it may gain value over time. So in this case, 1 divided by lambda p plus 1 minus k. Well, let's take one example. K equals to 5. So what? We have 5 elements, right? 0, 1, 2, 3, 4. And what? Absent 0 equals to what? Lambda 5, 1 divided by lambda 5. And absent 1 equals to 1 divided by lambda 4. So basically, you're using the future eigenvalues to define the previous gains. So this is a non-causal theory. This is not realistic. So let's suppose this is an unusual case. So we don't know the eigenvalue of Laplacian. So we suppose the estimate value is L as L0 with eigenvalues, L of lambda of I. But the true Laplacian value is L plane. So it should be the real value should minus the estimated value, and value should smaller and equals to sigma r, which is the ideal frequency, usually 1. And as protocol gains the epsilon k using L of 0 and repeat n minus 1 step. So it basically means we do the filtering again and again. And the error may satisfy. The error may occur because as you can see the formula, it basically means what? E of j times E n minus 1 is the eigenvalues of all the sets over time. It's less than equals to this one. It's basically 1 and times a constant. And the constant is smaller than 1, which is not realistic because, well, realistically, most frequencies are not minus. It's usually bigger than 0. So that is just not realistic. And this is another unusual case. Assume we don't know the structure, unknown topology. Assume only maximum known degree. D bar is known. Design periodic gains of length T0 over 0 to D bar. So convergence may occur over time. And let's assume lambda 2 bigger than the value of adjacency matrix and is bigger than 0. And the consensus error may satisfy as below. And this is actually similar to a previous case because we don't have frequencies that is smaller than 0. So this is not a realistic case.
To implement the MATLAB, we follow the paper and design. This is the first figure. It's the relation between the time step and the state of 6-agent network over the discrete time step ranging from 0 to 4, while the vertical axis is scale from 0 to 1. The trajectories clearly demonstrate that under the distribute consensus protocol derived from the graph signal processing approach. All the agents convert to the same state by the step 3. Then we move to the second figure, which illustrates the evolution of the state trajectories for 6-agent network under the consensus protocol design via the graph signal processing approach. In this simulation, the state of all agents remain nearly ligand and close to 0 from the initial time step up until the time step 55. This behavior initially confirmed that the design protocol filter acting as a low-pass filter effectively suppress the high-frequency components, thereby driving the system toward an average consensus. There's a mistake because it doesn't approach from the 0 to 60, but I think it doesn't matter. It doesn't matter. However, after around the 55 time step, the graph shows the market divergence and contemporary behavior among the agent states. This emerging instability indicate that the periodic gain scheduling, while acting as reducing consensus error in the early stage, introduce dynamic instability later on. In other words, if the periodic gains are not carefully tuned, the filtering effect may overshot or even destabilize the consensus process, leading to an oscillation and divergence on the agent state. So here is the conclusion. So the first convergence is the direct result of the design protocol filter that acts on a low pass filter. It perfectly prevents the zero frequency component while eliminating the higher frequency component. In other words, by filtering out the discrepancies, the control gains effectively drive the system tower average consists in a finite number of steps. The result confers the spherical prediction that if the design filter satisfies this three. It is it must satisfy these three equations. Then the multi-agent system reach the constants with infinity time. Here, the simulation on 6-agent cycle clearly validates this idea, showcasing how each agent synchronous its state, aligned with the overall network average by times step 3. In second paragraph, its behavior initially confirmed that the design protocol filter acting as a low pass filter effectively suppressed the high frequency component, thereby driving the system tower on an emerging consensus. So overall, second results underscore the critical balance required in selecting periodic control gains within the graph spectral framework, ensuring that the filter animates the high frequency discriminant without the right density triggering instabilities over the extended time horizon, particularly in the uncertain or variable network topologies. So here's our information are mainly from the midterm project. So not so much from internet. So here's our report. Thank you very much.
Here are some comments for you. Number one, it is not really necessary to put your ID number on the outer page, okay? It is not really necessary. It's not really necessary, but it's fine. And then again, I refer you to itemize all the contents. Put a bullet in front of the top. Okay, or item, whatever the shape is. Okay? So that will bring attention to the audience. Okay, here is the point number one I want to say. And this is point number two I want to say. Okay? So itemize your statement. Okay? And also try to reduce the words. Use fewer words, just show the key ideas. Okay? And then this catalog is too much.
Oh,
The design. Well, I just say that
because you said the last time we need to add the catalog.
I haven't been, no, that's in that. Okay, anyway, this is really too much, sorry, okay? Try to simplify your layout of the slide, okay? You don't have to give a very proud, during design, you don't have to give a very proud layout in your slides, okay? Okay, and then, let's see. Some arrangement, that's a good idea, okay? This kind of good idea. Okay, you catch the graph and also point out the key ideas, what you want to say. That's a good idea. Then the is we have limited time, so let me jump to the main point of the page. Okay, this the figure on the graph on page, let's see, 16. I think you have spent a few words on what happened here. Okay, but to me, it's still not so clear why it diverged. Okay,
So basically, we don't know the structure, so we cannot determine each agent's values. So we just assume it starts from 0.
yeah, sure, that's fine. And then eventually it diverged. The numbers read out, 10 to the 15. The numbers read out. So if it is possible, try to explain what really going on behind this phenomenon. Okay? And then for the reference, I think your reference, I think it's a little bit weak. Just one reference given in the slide. Maybe from my point of view, give say maybe 4 or 5 references at least will be a problem. Just one reference, little bit weak, okay? Give a little bit more reference, right? Okay, thank you. I think you also spend a lot of time on this. But why in the report? Nothing here. That's basic. All right. That's what we are. Okay. Lines. Yeah, the microphone's on. Oh, maybe we can take a break, okay? I think everyone's feeling tired. Okay, before we start our next presentation, I'm going to take a break, okay? Okay, we still have a few minutes, right? Don't worry. A stop. Oh.
Good afternoon, everyone. We're going to present our project, which called Audio Signal Missing Value Recovery via Low-Rank Approximation of Comparative Study of ILRA, TSR, and KDR. My name is Li Ping Yi, and my teammate is Ron Yu. This is our teamwork. Let's begin with abstract. So, like our title, we select three recovery methods to recover the missing audio segment in Phil Alisa. And both random and continuous missing patterns are stimulated. And although all three methods have some errors, but we still think that ILRA's result is more understandable and meaningful. And next is introduction. Missing signals are a major challenge in many domains. For example, in industry, missing encoder signals lead to equipment failure and mechanical damage. And in our daily life, losing Wi-Fi data can be very inconvenient. So how do we fix these problems? And in our midterm project, we covered a paper called Missing Value Recovery for Encoder Signals Using Improved Low-Rank Approximation. And this is focused on encoder angular velocity signals. Then we curious that can this recovery method be used to repair audio signals? So our contributions are select three representative signal restoration and define two missing value scenarios for audio signals. Then we analyze and compare restriction precision for each method. And audio signals are electrical or digital representation of sound. And the sound wave has four fundamental components, which are amplitude, frequency, phase, and waveform. And amplitude determines the value, and frequency measured in hertz determines the period of the wave, and the phase is the time shift of the wave, and the waveform determines the timbre. And when like this picture, O1 wave and P3 wave, it has different phase. And considering that vocal recording have more complex harmonic, so we selected Beethoven's for Alisa as the test sample. And this song played by garbage chart, so it's recognizable. And in paper we use for our midterm project, it categorizes missing data patterns in two types. Based on interference sources to random missing and continuous missing. And we keep this classification to recover the missing. And we can see that picture B is the random missing, and the picture C is the continuous missing. And I'll introduce that reconstruction method. And since the code involved is abstract, so I use the simple example to explain each method. And the first method is called TSR. And TSR originated from robust statistics, beginning with Peter in 1981, and finally formalized in 2009. And the first step is called window extraction and pre-processing. And we can see that the missing value is here. And the first step is to break the matrix into two parts. And the W1 has the missing value. So in this step, we need to leave out the missing value. So we only have W2 is complete. But the one matrix can work. So we create the W3 matrix from similar example for estimation. And then we combine the W2 and W3 matrix to PCA matrix. And then PCA fitting is for analyzing the variation pattern in new matrix. And we can get two values, which is main vectors and first principal component. And these two is important. And the third step is for projection. And we have W1 and the X sub OBS is from W1. And mu OBS and V OBS matrix is from the previous page. We calculate to get these two. And we can use these three values to calculate the score computation. And the score computation helps us figure out how much missing value has shifted. And so we can get the 4.34, and this is the final signal. And this is the flow chart of the TSR. And this is our code to recovery the audio signals. And this is TSR function. And we can see that break the matrix into 3 values. And we can reconstruct missing nodes using the PCA projection. And next is KBR. And KBR originates from Rubin's regression imputation framework and predicted missing value by extracting features from observed data. And we can see the example, we can see the first state, and the missing value is here. So we assume X is time and Y is signal, so we can write it as 1 and 1, 2 and 3, 3 and 2. And because the 5th element is missing, so this is the missing value. And we imputate the linear model fitting. And here we using these squares. Is the formula can calculate A and B parameter. So we can get the completed formula. And then we substitute the 5 into the formula, then we can get the missing value is this. And this is the flowchart of the KBR. And we use kernel-weighted regression here, not these squares. And this is more complex, but the value has more accuracy. And the third method is called ILRA. And it's the framework for recovering missing values in encoder angular velocity signal. And we have this matrix, and the missing values is here. Then we use initial imputation, and this example is used column min, but in practice we use cubic spline to do initial imputation because cubic spline is smoother, can have smoother value. And here is the next step is BDC. And BDC is we got the initial imputation matrix from the previous step, and this step can subtract the row and the column min to centering the data, so we can get the BDC matrix. And then it's SVD and rank 1 reconstruction. And SVD is to break the BDC matrix into 3 parts, and we focus on this sigma. This sigma is the value, is the matrix, is the eigenvalue of the matrix, and the eigenvalue take the square root can get singular value. So this is the BDC matrix singular value. And rank 1 approximation is we take the maximum singular value to do calculate. And then we can get this answer, and we update the missing cell. Only update the missing cell. And then we reconstruct time series, use PSR to unfold the matrix. And this is the flowchart of the ILRA. and we use relative error to check whether it's convergency or divergent. And this is the code we use to recover the audio signal. And we can see that qubit line is here to pre-imputation. And that's all for the recovery method we use.
Next, let's talk about our evaluation criteria. We use three main metrics to assist a correct of our reconstruction method: MAE, RMSE, and the cosine similarity. First, we have MAE. This metric tells us the average difference between our reconstruct signal and the original signal. We take the value of the error to avoid them cancel each other out. A low MAE means better and correct. MAE goes on the overall average error. Here the formula. Next is RMSE. While MAE gives the average error, RMSE takes the square of error every length and then takes the square roots. This makes RMSE more sensitive to large error, and it also retains the same units as the original signal. Just like MAE, a similar value means better and correct. RMSE is especially good at detecting extreme deviation or outlier. Here the formula. The third one is cosine similarity. This metric evaluates how similar the direction of three non-zero vectors are. It commonly uses the signal process and time series reconstruction, which makes it a good fit for our experiment. Cosine similarity close 1 is mean similarity to the original signal. 0 means non-similarity, and -1 means completely offset. The formula is here. Now we move on to result and discussion. First one is recovery of continuous missing value, and the other is the recovery of random missing value. Let's look at the code. We use mandate just like return, and we use the famous melody, Fear and Lisa. We use frequency to represent a pitch, and then we convert it into a sine wave. The part K plus 2 means a segment of 3 continuous nodes which we treat as a missing section. Below that, we apply 3 reconstruction methods: PSR, KDR, and the ILRA. Next, the top MA and the RMSE we calculate. Since this process is quite computationally kept and includes plotting, it runs a bit slowly. So we directly print the MAE and RMSE of 3 methods in the command window. We also calculate cosine similarity. We add the audio output button at the end so we can actually listen to the result without playing later. Here the output of MAE and the RMSE in the continuous missing value case. Again, the smaller the value, the better the correct. Also, you can see the difference between methods are very small. Interestingly, ILRA was not the best performance, which goes against our theoretical expectation. We believe it is because the missing segment is too short, making it hard to highlight the strength of each method. Look at the concise similarity. A higher value mean more similarity to the original signal. Once again, all three methods perform a similarity, and ILRA isn't the top performers. Now let's check the background. Red indicate high energy and blue indicate weak signal. You can notice higher vary because each note has different pitch. The first image is original signal. Each line represents the note. The image below is the recovery of three methods. Among them, KDR, which performs best according to our metric, show a mix of light and dark blue. It without clear, identifiably reconstruction pattern. In contrast, ILRA management a partial reconstruction manifold signal component. Here the audio output button. This allows us to listen to each version of the signal. Let's start with the original signal. Now here the version with continuous missing value. You will notice consecutive bits are missing. Now the TSR version. And KDR. You may be wondering why it sounds almost the same as the missing value. Well, as we saw in the background, the recovery signal area are almost blue, meaning the energy is too weak. That's why we can't really hear them. This is something we can infinitely improve on the future. Let's move on to our second scenario. Most part of car is the same as the continuous missing value. Let's focus on what's different. Here, random means randomly select three non-consecutive notes to be missing. The result of the process is the same, so we won't repeat it. Now let's look at the result. Unfortunately, ILRA still did not perform the best in the random missing value scenario. In cosine similarity, score was similar to what we saw in the continued case. However, in the background, compared to KDR merge and the blurry reconstruction, ILRA once again showed more promising recovery, while more distinguishable feature that suggest potential for further improvement. Conclusion. Unfortunately, the output result of the experiment didn't meet our expectation. According to the evaluation metric, MAERMSE and the cosine similarity, ILRA didn't show the best performance. Also, the difference between CSRKDR and ILRA was quite small. We believe its main issue lies in the short input signal line, which made it hard to see significant performance difference. Additionally, the reconstruction signal had a noticeable lower energy than the original, which is another area we need to work on. Here are our This concludes our presentation. Thank you for your time and thank you for your time and attention.
All right, a few comments again.
Okay, a little bit over time. Okay. Now, basically, I think you all did a good job, right? Spend lots of time on this and you can do that. Okay, first point I want to mention is, I think I haven't mentioned this in the other case. Usually, when we are presenting a research paper, we will give a brief review to some existing papers. Okay, that's called paper review or literature review. Okay, why we have to do that? Because this study that you are doing may not be the first one, may not be the very first in this field. So you are going to tell people that what is your contribution to this type of problem? Okay? The other people, they have done this, and now they're going to improve whatever they haven't finished, or whatever the weak point, or whatever the shortcoming they have. And then you are going to overcome the difficulty, or you are going to improve whatever they have done before. So this is the literature review. You have to tell the people, now we are here. We want to do something to improve whatever the people have not finished. So that's the value of your research. Okay? So literature review is very important. Okay, and then once you have the literature review, you are going to give the introduction. That's good, very good. And also you give a very good type of presentation. You give a figure here and then try to illustrate what you are going to do about this kind of problem. Okay, that's very well. And then in most of the cases, we don't show our code to the audience because, again, you don't have that kind of time to give a detail to tell the people, well, this is a code, and from here to here, I'm going to do whatever the algorithm. Okay, so honestly, it is not really necessary to present your code in the slide. But you can attach, like I told you, you can attach your code in the paper. And you can attach the code in the paper. But now you have to attach the code to the slide. You know, the slide takes lots of time to do that. Right? So that's why you hold the time. Okay, and then let's see. You compare all the three different methods, and then you told us the ILRA is not the worst one, or the but to me it looks like they are quite similar. All the three methods, they are quite similar because like the number you showed on the figure here, okay, on the chart, 0.707043, 0.707043, 0.707044. The difference are quite small. It is not really this one. It's really hard to say that which one is better than the others because you only use one example. if you really want to compare, you have to run maybe at least 100 examples. So you have to go through the, we call that kind of Monte Carlo simulation. You have to run lots of numerical examples and do a statistics. Okay, you have to do a statistic analysis because it is not fair to say, based on just one example, then the method A is the best, method C is the worst. That's not really fair to say that. I have to say that. Okay? So that's a major point I want to remind you. Right? Okay. And then the reference good, but usually we carry the number in front of each reference. So the first one will be square bracket 1. Second one will be square bracket 2, and so on and so on. Okay? That's the kind of convention. Okay, but anyway, you did a good job. Okay, you explained lots of time on this you can tell. Okay, thank you. Good. Very well. Okay, finally we had team number 5.
Hello everyone, we're going to talk about enhancing MCNN for FHS signal classification with transformers and learning structures. Further aspect, in this presentation we'll outline our approach for classifying FHS signals for accuracy. We explain why rectangulary CNN filters are useful for high frequency data, how transformers improve feature modeling, and how frequent learning helps with noisy data. Finally, we show our simulated results. And before the FHS introduction, I'm going to easily talk about the FHS and the MCN. First, there are 3 types of FHS. The first one is time and frequency. And the second one is frequency power. And it also means the signal strength. And the third one is called quantum map. And the third one, how quantum map is used by it has helped about the outcome, and it means that the front is now regularly appear. And in later we're going to talk the type of FHS is the time frequency. MCN is like the model that we're going to use on the FHS. And also the transformer encoder is similar using like the MCNN. Now I'm going to talk about the FHS introduction. FHS stands for frequency hopping spectrum is a technique where signal frequencies in a procedural random pattern. This provides some security against jamming or interception. However, this frequency hopping nature makes FSS difficult to detect and classify, especially under noise conditions like low signal to noise radios. Then our approach begins with a multi-CNN architecture that uses rectangular pictures to match the time frequency representation of FSS signals. To go further, we add transformers encoders for global pattern modeling, and we provide two strong data augmentation techniques, XR and coordinates. And this tool is just like let we to know the final result more clearly. And finally, we adopt programming learning training our model gradually for easy high SNR to high low SNR samples. And this is our architectural overview. The spectrum frame of the signal is passed through MCN layers followed by a transformer encoder and link chassis. This hybrid design helps the model learn by local and long-range features. It's particularly useful for time frequency data like FSS.
Okay. In these tables, we can compare the performance of three models. The yellow one is a base CNN, and the orange one is NCNN. And finally, the magenta one is NCNN plus transformer. That's our model. And we can see as the SNR increases, performance drops in all cases. But our model remains accurate even at -5 dB. And at -2 dB, we achieve over 85% accuracy. That's a major improvement over the baseline. Okay, and this one is our confusion matrix. It can show our model differentiates between FHSS types and background noises. And most samples are classified correctly. And these classifications are mostly among similar FHSS types. This shows the model has learned meaningful and robust features. And the next one is our curriculum learning. The curriculum learning is inspired by human education. We train the model to focus on the high quality data at first, and then gradually learn from the harder cases. This improves convergence speed and generalization ability, especially in low SNR scenarios. And this is our model's strength. First one,
Our model can capture both local and global TFR features. And the second one, our models has more resilience to SNR degradation. And the most important one is, in our models, it can actually work in a real world cases. And also our models are more benefits than the normal cases, but it still has some challenges. Like it will have high computation costs from transformers, and it need for diverse and realistic data sets. And this phase is future work, but we'll just skip that. And last but not least, these are the references that support our work. We will very appreciate they we are really glad to thank the researchers who introduced MCN and Transformers modules. And that's our presentation. Thank you for paying attention.
Okay? Any other comments here? Okay, a few comments for you. Number one, in your title you mentioned that this is about the MCNN or HHSS, signal classification and transforms, and learning strategies. Okay? And then in the presentation, I didn't see too much. I didn't see actually any about the MCNN. What is MCNN? What does MCNN stand for? Okay, and you did not give an introduction or explanation of that. You just use a word. I think that's not enough. Okay. Besides, through your presentation, you mentioned about our model many times, but what is the our model? It's not so clear. What do you mean your model or our model? I didn't see that. Before we didn't see that very clear. Okay? Because that's a major point in your presentation. You have to show your model to the audience based on my method, my model. This is my model. So we have this kind of result. Okay? And then I have to ask you, did you really run true data? Did you generate true data and then use your model to clarify or to generate this feed or any conclusion data? It is generated by your own model, your own data. It is generated by your own program, let me ask you this. Did you create real data and then run your program, run your code, and then generate this feed? Or just copy from some other paper? I don't know. Your paper. Okay, let me say that again. Did you generate real data or simulation data? Let me say that, okay? And then run your code, run your MATLAB file, and then create this feature. Is this from your own program? Did you generate this feature from your own program? Did you run the program, create this data? Or this is a feature taken from
some other things, I don't know.
The code is not mine.
Because to me, it looks like this figure is not generated by MATLAB. So no, I'm not sure. I'm not sure. I said I'm not sure. Did you create or did you generate this data by yourself? I mean, by the code you wrote. Or this is copied from somewhere. Maybe use the microphone. Okay? There's a microphone. Okay, maybe you do
I have done the code for FSS and I have done the code for FSS and for MCN and I run the MCN for this also include the FSS. And this data all I have input for the resident number.
So this figure is generated by your own code.
Yes.
Okay, then what is the model behind this? You didn't say too much about your model. Just use the word, our model, and MCA and so and so. To me, it looks like it's too rough to say that. Because we want to know how did you do it. You have to, we really want to see that. Let me say that. We are interested in knowing your method. Okay? So it is better to give us more detail. How did you develop your algorithm? And how do you implement your algorithm? Okay? So I would prefer to see that, even though it's done. I would prefer to say to see that you give a introduction to the MCN, and also CNN, convolutional neural network. And how do you combine, or how do you, what is the word to say that? Okay, use the word. MC and cross transformers. Okay? So I'm not quite sure. What is your model? Again, go back to the basic problem. What is your model? It is not clear. You have to specify that first. So based on your model, so we have the following algorithm for mathematical equations. And then we generate the data, whatever data it is. You have to give us some explanation about your data. Okay? So this data I use for this data. Okay, I generate. I use CNN, I have whatever the result. I use MCN, and then what's that? Okay? And also, the classification accuracy. I have to say that. That means you have run lots of numerical examples, but I didn't see that. Okay? Because the vertical axis means classification accuracy, right? So, which means you have maybe more than 1,000 examples, because you have to explain your CNN neural network. In order to explain your neural network, you need to run more than 1,000 examples, or even 10,000 or 100,000. And then based on those examples, okay, you have go through, use many examples. Suppose you use 10,000 examples, numerical examples, and go through CNN or MCN. So you have the coefficient for each
then you have another maybe 200 examples, 200 verbal examples. You use the 200 examples to go through the CNN in the trend, and CNN in the trend, and see, well, these are correct percentage or incorrect percentage. Maybe among the 200 examples, CNN gives us maybe 80% correct percentage. And then MCNA gives us, I don't know, maybe 79%, and so on and so on. Okay? So that's what I said. You have to give us a very clear, all the details, let me say that. How did you generate the data? Where are the data? What are the data? So I don't know. You didn't say that. You did not mention that. What are the data? Okay. Then what is MCNN? How did you combine MCNN plus transformer? You didn't say that. And it's wrong. Okay, and then I'm not sure, how did you construct this confusion matrix? Yeah, How did you construct this confusion matrix? I'm not sure. You didn't spend much time on that. Okay, and what is this useful? I'm not sure. Okay, so you have to give us a few words about this. Okay, how did you implement this confusion matrix to your network, or to your model? Okay, so give us a detailed explanation of that. And then finally, I think you missed a very important slide, conclusion. Maybe the last slide, before this one. Sorry, previous. Yeah, here. Maybe this will be the conclusion, I don't know. It is better to give a conclusion. To tell the people, well, based on my method, I can achieve this. But my method has the following okay, I mean, shortcomings or benefits, like you said, strength. Okay, so this belongs to your part of the conclusion. This method is good in the sense of availability. Okay, and this method is not so good because of certain people find it based on your reversal flux. Okay, got it? Right. Okay, and then finally the reference here. Again, I think it's not quite complete. It's not quite complete. Okay? If it is a paper, then you have to mention the journal, journal type. Okay, and also the year, model number. Okay, and item number, so and so. If it is a book, then you have to mention the publisher. Okay, all right. So similarly, this is to everyone. Whenever we are using reference or we are going to generate reference, please use a standard format. Because this reference format is not created by me, by you. They are created by someone else already for more than 100 years. So it's kind of conventional. Okay? So don't argue with me. Well, I think this is good for me and I prefer this one. You have your own preference, that's good. But every conference has their own reference format. Every journal has their own reference format. Okay? Even a book. If you want to publish your book in, say, Pearson or Wiley, they will tell you, please follow my format. Okay? So you are not allowed to generate your own format. Okay? That's important. So keep that in mind. Okay? All right, thank you. Okay, I think we have finished all the presentation. I have to say that most of you, all of you have done a good job, okay? You have spent a lot of time on this, I appreciate that. You spend lots of time on reading papers, writing your code, and writing the paper, and those are the slides, right? Okay? I want to push you to your boundary. I want to drive you to creative, okay? I want to drive you to a creative application. Because I think you can do that. I think you all can do that, okay? So give yourself a higher standard, that's what I can say. Give yourself a higher standard, all right? And if you are interested in doing the research, you can follow the research you have done in the following couple of years. That's good topic, okay? All right, so that concludes this report. Thank you everyone for coming to this class. Thank you for your attendance. Okay? Thank you, and have a good long vacation. So see you all after the vacation. So you will be graduated, right? Good. Congratulations. Okay. All right. So thank you everyone. Have a good evening and have a good night. And have a good weekend. Gentlemen, why don't you see your